it. I'm numb, I'm stupid, I'm staying. And if Cupid's got...
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. Here's an example how we can use the equivalence of work and energy to investigate a spring mass system like seen on the left here. So we have a slider on a table. There is some friction acting on it also, like this F mu, and it has initial velocity to the right, and let's say it comes to rest in displacement d, and we would like to know what is the magnitude of the friction coefficient in this case, and initial velocity is v1 as shown here. So what is the net force done on this slider as it moves to the right? In addition to the friction force, there's of course the force from the spring that also points to the right. So draw it here on to the left, and this is, as you remember, its magnitude is kx. Because the spring is being stretched, it slows down the slider. So what is the net work? Or let's put it this way. Work done by the spring, and this is important, on the object, not the other way around. It has to be negative because the force that is exerting on the mass or the slider is in opposite direction of that of the motion. So because the work was F dot S, if these are in opposite direction, it has to be negative. And the magnitude is, in this case, half times k d squared. So as the slider is slowed down by the spring is storing the energy in itself, and hence it's sucking that energy from the object. Hence the negative sign here as well. And work done by friction also on the object, and again that is in the opposite direction from the displacement, so it has to be negative, and its magnitude is mu times the normal force times the displacement, and normal force is just mg, like this. And now the principle of energy and the net work done on the object. The net work is equal to the change in the energy of this slider. There is only kinetic energy concerned with this slider, so E kinetic, and the difference of any quantity always calculated as final minus initial. So what is the net work? So it's the work done by the spring, so minus half times kd squared, plus work done by the friction, oh, of course there's a negative sign there, minus mu mg d equals the final kinetic energy, well that's 0 because it has come to a rest, and the initial velocity or the kinetic energy half times m v1 squared. We are solving for mu, so we'll isolate that, multiply everything by -1 to start with, and then move this one to the other side, so we get mu mg times d equals half mv1 squared minus half times k d squared. And mu is mv squared minus kd squared divided by 2mg d. A few sanity checks. Let's say we increase the stiffness of the spring, so K increases, so which brings the value of the mu down, and that makes sense because with a stiffer spring we need less friction to bring the object to rest. And on the contrary, if we have a higher velocity to start with, so v1 squared increases, so that leads to the increase of friction because we need more friction to bring it to halt in the same distance. So at least for those parts, this results seems to make sense, and we are happy with it.